Our next speaker is Michael J. Redding, CTO at Entropy. Today, Michael will take us on a journey into the world of quantum entropy and its role in strengthening cryptographic security. As AI and machine learning introduces new risks, Michael will highlight the growing need for high quality entropy in cryptographic systems. He'll also cover recent advances in the commercial market for quantum random number generators and share immediate applications that can reinforce our security today, well before a full transition to PQC. Please join me in welcoming Michael.
Hi, I'm Mike Redding, and I am the Chief Technology Officer of Entropy, a Canadian cybersecurity startup. And what I'm here today to talk about is how you can leverage quantum entropy to boost your cryptographic security. So in this talk, we'll first talk about the threats that arrive from weak or poor entropy. We'll talk about sources of good entropy, both traditional or classic and quantum sources. And then to make this news you can use, we'll talk about specific security use cases where strong entropy can harden your cryptographic and network data and server security. So that's our agenda for today, and I'm excited to share this story with you. So to get started, what is the risk of weak entropy? And you'll often hear people use the kind of loose term, bad entropy will break encryption. So first of all, what is entropy? Entropy is randomness, it's noise. It is the destructured state of the universe over time. And what's important is that when you have randomness, that translates in binary into random bits, ones and zeros, which ultimately manifest themselves as random numbers, unguessable, uncalculable, and that becomes the basis of cryptographic keys that are used to secure our data and our networks and our systems. And so the whole idea is, if you use a lock and key metaphor, bad random or bad entropy means you have a weak key, means it's guessable, it's copyable, it's repeatable, and you can effectively pick the lock. So bad entropy doesn't break the encryption algorithm itself, doesn't break the math. It just means you can pop the lock at will and therefore render, no matter how good the algorithm is that's protecting your data or your system, you can render it breachable. And so that is the root problem. That's how you break it, is you pick the lock. And so is this a thing? Is this a concern you should have? Well, I'm going to walk you through a number of documented attack vectors and breaches that have been documented as being the result of bad random or weak entropy. And we'll start with a study from a few years ago where they basically scanned the internet and looked at TLS servers and SSH servers. They scanned over 12 million on the internet. So, a small sample relatively to internet sizes. And what they found, that as many as 1%, over 100,000 SSH servers had poor key constructs, meaning they were built from weak entropy, so they were guessable or calculable, and as a result, you can access them maliciously. So that's a tip of the iceberg. The next example is more recent, and this was done by Keyfactor, where they went out and looked at X509 certificates to say, hey, what's out there? What are on a lot of embedded devices? Because that's a particular focus of them. And what they found, that 1 out of every 172 RSA certificates, so this is in the millions, are based on weak random numbers, and as a result, could be forged, could be compromised, resulting in breaking of trust and spoofing or malicious access. And so a very large problem set when you think 1 out of every 172, when you think just in the consumer example, the average household has maybe dozens of devices. several of them might be compromisable through a bad certificate caused from weak key generation and random numbers. Those first two examples were specifically looking at digital certificates or digital signatures. Now let's take a look at the gold standard of security, which everyone talks about, which is AES 256. And the 256, of course, is the number of bits in the symmetric key used to protect data in motion and data at rest. And it was an interesting study that showed that, everyone said you should migrate from AES 128 to AES 256, but it's not just the length of the key, but the quality of the entropy. And what this study showed, that out of those 256 bits in your key, if you didn't have at least 220 bits of truly random entropy or random number, then basically you could calculate that key in real time, like trivially amount of processing, relative to today's computer horsepower. So I don't even need some advanced, supercomputer or quantum device. I could compromise any key with less than 220 bits. And that leads us to a very important concept, which is the entropy rate, which is the amount of true entropy divided by the key length or the bit length to give you a ratio. And in this case, what they found is that if you have a ratio of less than 0.85, you are susceptible to these attacks. And that entropy rate is something you can now look at your entropy sources that you're using in your enterprise and ask the question, and every vendor of a random number generator that's certified has to specify its entropy rate. If you find it less than 0.85, it is not giving you sufficient security as shown by this particular attack. So a very important benchmark to consider when choosing entropy sources, which we'll get to in a few minutes. Another example, just to keep piling on, was a study that was done where we're using our new friend machine learning, also called AI in many cases, where they scan the internet. Large learning models have shown us a methodology where you can basically read the internet, and that's what they did. And here they looked at over 250 public X509 certificates. And across that basis, they found about 113,000 duplicate devices. And unfortunately, these were all from a singular manufacturer. And what that meant is that if I had a device from this manufacturer and you went down the street to a surplus store and bought another one, you'd have its twin. And as a result, because you had its twin, you could access my network. Think about government, banking, military. That is very problematic. And again, the root cause, bad random numbers to generate those certificates. And last but not least, to put a monetary figure on it, there was a study done and they called the breach Randstorm, where a number of Bitcoin wallets were built using a bad random number generator, so weak entropy. And the net result is that someone could maliciously access those wallets. So if they're a true cold wallet and never on the internet, never connected to the network, they were safe because they're air gapped. But the second they are put onto any chain, they are vulnerable. And the estimate was about, at the time of the study, at the price of Bitcoin at the time, was about $1 to $2 billion up for grabs, just waiting for the vultures to jump on it. And that's real money. And when Bitcoin goes up, then the size of the prize gets even bigger. So there is a monetary incentive for attackers to exploit this weakness. And I just saw another study, a completely different vector, looking at the asymmetric encryption at the heart of Ethereum and Bitcoin, where again, poor random number implementation, there the researchers could identify, and just by reading the public chain, pick out wallets that had weak signatures and therefore weak encryption. They went and visited those wallets and found they'd already been emptied out. And their estimate was over $30 million was looted by malicious attackers using and exploiting the weak signing caused by weak entropy. So real money, real systems, real scale. this is a pervasive problem that is avoidable. As I mentioned earlier, the thought is that, weak entropy can even cause breaches of the most advanced algorithms. And this was from a talk in August where NIST was sponsoring the new post-quantum algorithms. And here researchers were talking about, the latest cryptographic attempts to breach these brand new asymmetric algorithms, which are based on lattice-based cryptography, and specifically an underlying mechanism called learning with errors. And the news that gives us all comfort is that these cryptographic researchers could find no ways to breach the algorithms themselves, but a side product of their crypto analysis was, once again, no matter how good these new NIST post-quantum algorithms are, if you start with bad random, you basically make key recovery and breaches trivial. And you can see they said the words very easy. And it wasn't just one mechanism. They actually found two completely different attack vectors that would just, chew up and spit out the results if the key started from poor random. So no matter how advanced the algorithm, it's again, if you start with weak raw materials, doesn't matter what you build after the fact. So recapping, a lock is only as strong as its key. And so just like your password shouldn't be password 123, your random numbers shouldn't be guessable or calculable or repeatable. And so what technologies can you leverage to actually do something about it? And there are basically two types of random number generators that you can choose from in order to get what you need in terms of random number quality. The first is a hardware-based random number generator where some physical process is used. It can be heat dissipation, it can be radioactive decay, it can be some quantum effects, which we'll talk about more in a second. But it's a physical process that is provably or calculably unique, unguessable, unpredictable, and that is what generates electrical or other signal that can then be translated into ones and zeros and a random pattern, and then that becomes your basis of entropy for building cryptographic keys. The other is software, because you don't always have a suitable hardware device. And so you can do it entirely from softwares, and you'll hear the term DRBG, or deterministic random bit generator, is the more expanded term for this class of software. Often they are a variant of a symmetric algorithm, and there's a lot of mathematical reasons why, which we're not going to dive into today. And those are called pseudo random number generators because they're based on some structured mathematical process, some software algorithm. They are only pseudo random because there is ultimately some predictability, and that can lead to challenges. And so we'll talk about that a bit as well. And very importantly, one of the things that is, as you start especially thinking about hardware, if you're using an expensive or exotic source to generate, not every device, not every laptop, not every edge device, especially think about cheap and cheerful sensors that you may not actually have these hardware devices on board, and software may be a challenge. And so if you invest in strong generation, you may also want to think about, how do I move it from where it's created to where it's consumed? And whether that's the system bus inside a processor or across a cloud infrastructure, secure distribution, because what's the point of a gold bar if I put it in a paper envelope? So when you talk about hardware generation, you'll also a lot of times hear folks call hardware generated random numbers true random numbers, or TRNG or TNG, acronyms. It's technology, so of course, in computers and IT. So of course there's lots and lots of acronyms, but true random numbers are generally used, to refer to something that comes from a hardware source, and it can be anything. Famously, Carnegie Mellon put together a wall of lava lamps and used webcams, and the state and shape of any given blob in a lava lamp is, random or pretty darn random, and you mash a whole bunch of them up together, that approaches true randomness. And so, hey, it may not be fast, but it works. And so that's one example. The latest, iteration of this is to move from classical processes to quantum processes. But classical processes, like I mentioned, might be heat dissipation. It might be, some people have used keyboard clicks and mouse movements from humans, because how do we guess when I'm going to hit the letter T and how hard and how often? Those are things that are approaching randomness. But the idea is it's non-deterministic. Like, you can never determine what come next. And the evolution is from these classic, or ring oscillators is another one, these classic sources to quantum phenomena. And I'll double click on that in a second. But the idea being that quantum physics is spooky and weird and unpredictable. And, even Einstein said, nobody understands it. And if you can't understand it, you can't guess it. And therefore it's even stronger, right? But importantly, even the most random physical sources can have some bias, which means if you flip a coin, it's never 50-50, because each coin has a little bit of imperfection. That means it's not perfectly 50-50. So no source is considered perfect. And therefore it is very acceptable, and we'll talk about it in a minute, to use a little software to clean up the hardware and to try to take out and scrub those biases. And it's called conditioning or whitening. And that is perfectly acceptable. So some folks will tell you, I don't need any of that. That's great, but it is perfectly acceptable under all of the current standards to polish up the raw materials. Again, it's like refining the ore. Now, like anything, there's many kinds of hardware sources. And so the URL here you can click on leads you to, or you can search on those words. You'll find a great report that was done that tries to give a taxonomy of all the sources of physical randomness. Good luck. It's a maze, as you'd expect, because there's many ways to solve this problem, and it's very important. But often this is really for the random number engineers and the random number wonks. It's good to know this and be educated, and it's out there. And so great, you can have kind of a decision tree on what the different sources are, so you can classify it. And I wanted to share that as a reference for folks. But in particular, since this is an advanced talk, we want to talk a little bit more about the emerging science of quantum random number generators. And we're starting to see, it's still early days, and to say that we've even come close to inventing all the quantum mechanisms would be laughable, but they're already in the market a number of mechanisms that are specifically kind of leading the charge and are seeing early commercial adoption. And probably one of the most significant are photon-based methods. And one of them uses photon detection. That's probably the most common that you'll start to see, especially in devices that can be embedded in a server, that can be delivered as a PCIe board, or even in some cases as a chip that gets put into an IoT device. And so probably I would suggest the most prevalent mechanism in use today. There's also entanglement, where I actually entangle two photons and then stretch their distance. And you'll see this is often used with dedicated fiber optic connection. So it's not always dedicated. And that's a big focus of quantum key distribution, which I'll talk about more in a few minutes. And importantly, this is being seen as a strong way to do key distribution. But the challenge there is the distance over which you can maintain the entanglement. I think the world record has been between the ground and satellites. And so that's been done a few times now at a very low bit rate, like 1 bit per second. So not exactly usable for, say, browsing on the internet or securing high-speed trading, but proof of the physics always leads to then engineering implementations. Other use cases can be things around photonics, can be laser phase noise. Then you can look at other non-optical solutions like vacuum fluctuations, electron tunneling, again, very promising for compact implementations at the IoT or hardware level for putting into servers of today. And one I didn't really mention, but if you delve into the realm of quantum computing at all and looking at it for qubits, one of the big topics there is the noise generated, the noise that as a result that you can't read the qubits because they're making funny states and making noise, and that noise can be siphoned off and in some cases used as a source of randomness as well. And so there's a couple vendors that are saying, well, if you've got a quantum computer like IBM Q, why not siphon off all that noise you're trying to ignore for computational reasons and instead use it for cryptography? Hey, it's kind of, reusing the waste. We want to be very green, if you would, proverbially. So as I mentioned, we're starting to see early stage commercialization, and this is no means exhaustive list. Internet search is your friend, but we're starting to see a number of vendors creating hardware devices ranging from, as I mentioned, PCIe boards from like Quintessence Labs, ID Quantique, and Asymmetric are doing it at the chip level. Crypto Labs has a really interesting solution where they've put it into a USB stick, so you can plug it into any device with a USB port, and therefore have an instant kind of flexible upgrade path. QCI, they've made an appliance, but they are one of the ones that started with noise from quantum compute. So again, it's a space that's evolving rapidly, some early proven solutions, but innovation by the day. So very exciting. And since we live in a cloudy world and a SaaS world, we're also seeing a number of vendors also providing quantum entropy as a service, where I can source, can generate it from these, exotic devices in one place, but then ship it over the network to where it's consumed, but securely. And folks like Quantropy, which is my company, but also Quantinuum, Encrypt, and others. And so the great news is, as you think about your infrastructure, your business applications, your applications, you've got on-prem and in the cloud, you've got hardware devices, you've got software solutions, everything to meet the modern infrastructure. And that's important. You'll hear the word when people throw around, kind of casually, crypto agility. This is entropy agility, but the challenge is if you can make it, but you can't use it in the right spots, or you don't have the right form factor, then you're missing an opportunity. So the great news is the market is giving solutions that really fit almost any deployment scheme you can come up with. The industry's got you covered. And that's important to make this practical. And so I'm going to go a little deeper on quantum entropy as a service, just to kind of bring that to life. And this is a typical architecture. And in this case, we're represented as 3 tiers, as you'd expect from any kind of modern scalable hyperscale architecture. You have a generation tier. This is where you plug in, and the kind of going rate these days, and changes by the minute, but you can kind of think about 1 gigabit per second hardware device will run you, $6,000 to $10,000, today. And prices change as things commoditize. But think about 1 gigabit is $6,000 to $10,000, and so therefore you might want to invest in kind of a core generation facility and then distribute it out over the network, because I can't put a $6,000 device in my iPhone or in my edge sensor. So I'd want to invest in it upfront and then distribute it. You have a distribution tier that acts as the caching and scaling and buffering, so that you're not trying to pull against the direct source. And then, of course, you have everything from firewalls to laptops to mobile devices to cloud. You want this entropy everywhere, wall to wall in your enterprise, so no device doesn't have access. And so IP networking as a distribution mechanism makes a lot of sense. And to show you that this isn't just an academic or conceptual theory, this is just a screenshot from a visualization. This happens to be Entropy's, my company's key space secure platform. And here we're generating random numbers in Ottawa, Canada, where I'm based. And there we have a rack of Entropy devices. So think of it as an Entropy farm. And we're quantum securely streaming it over IP networks across the globe. When we ran this particular test, we were streaming to Singapore, Frankfurt, London, and Amsterdam. And what's interesting is I then double click on the particular stream from Ottawa to Frankfurt. And if you look real closely, you can see we are achieving a key rate of about 190, just about megabits per second on that one stream. And you say, is 190 megabits of entropy a lot or a little? Well, I'll help you frame that. And this is the way you can think of it. Google.com, people doing searches, there's net metrics suggest Google does about 64,000 new sessions per second on average, plus or minus. So 64,000 sessions, each needs to be protected with a symmetric key. AES 256 says I need a 256-bit key. So if I do the math, 64,000 times 256 bits per key means Google needs about 14 megabits per second of new entropy to satisfy all those needs. And so that means this one link from Ottawa to Frankfurt over transatlantic cables using the IP infrastructure is about 12 to 13 Googles. So that one stream would support 12 to 13 times Google's per second requirement. So that could support 12 companies or 12 use cases the size of Google. And as you can see, we're running multiple streams simultaneously. So this is hyperscaler. This is enterprise grade. And of course, there are others in the market offering similar capabilities, but it's important to realize this is ready for prime time. This is not just a thought experiment. So moving on from hardware to software. And again, this idea of pseudo random number generation or deterministic random bit generators. And the important is that it's done through computational. You seed it with some sequence, but because you heard the word deterministic, that means same seed, same sequence. And that is a risk that if you start with a bad starting point, it's guessable. There have been breaches in the past where especially people had little dongles, they were supposed to be generating random numbers. But once attackers knew the seed, they could guess the sequence and basically render that solution, breachable. And so that becomes the risk of if you don't start with a strong seed, the algorithm itself doesn't produce good results. And so you want to look for periodicity, meaning how often it doesn't repeat. And we're now starting to see the evolution from classic algorithms to quantum algorithms, just like we're seeing it on the hardware front. And there, for example, from Entropy, we offer a pseudo quantum random number algorithm that has a periodicity of 10 to the 500th years, which means it only repeats from a single seed. It only repeats the random number sequence every 10 to the 500th years, which is a long time and therefore unbreachable. And so that's the kind of technology where if I don't have hardware, I can go to software, and the evolution of the science of the software suggests we're always going to have stronger sources. So what random number? Like, again, you saw those examples I gave earlier where blockchain based on bad random number generators made for people stealing your money. And so here's a simple chart for true random numbers versus pseudo random numbers, kind of summarizing many of the points that I've made. I'm throwing it up here so you can refer to it later. I'm not going to drain it because I've hopefully already covered this to a great extent. And standards, right? What's the universe of technology and the internet without standards? And the great news is you can investigate this and you can ask the question of your providers, what standards do you adhere to? And our friends NIST in the US have thankfully put out a number of standards, SP 800 90A and 90B. You can generally think of 90A as covering the software and 90B, the hardware, and then C is in draft. And so if you're interested, you can dig in. And that's where we start to mash up hardware and software into kind of more complicated configurations. And so really trying to say, how do I have kind of a more modern approach to different layers like OS and application level. So 90C is very interesting, but A and B are crucial because they cover pseudo random number generators and hardware random number generators. And so understanding the certification of the sources you're consuming is a way to know you've got quality. And NIST has put forward testing. So don't take the vendor's word for it, test it yourself. So 800-22 gives you the standard suite to analyze the random numbers being generated and confirm that they are suitably random. So a lot of setup. Let's get into, great, I've got good random numbers. How can I use them? How can I use them today? How can I use them to immediately harden my cryptographic posture? And let's talk about that. So low-hanging fruit. The IET, of the Internet Engineering Task Force, has come forward with RFC 8784. So an internet standard that says basically if I'm using an IPsec VPN by mixing a strong random number in with my normal traditional classic key exchange mechanism, I can harden the cryptographic key that's used for a particular session and basically move it to a post-quantum security standard. And the great news about this is that can be done with some of the random number sources I've already talked about. It can be done on today's infrastructure. It does not require a migration to the just standardized new NIST algorithm. So it can be done with legacy classic algorithms that are already scaled out. And both the US and EU have said this does meet the criteria set forth in their various laws around quantum preparedness. So it is a instant post-quantum compliant upgrade that's standards-based. Say that 7 times fast, but that's actionable. And so to kind of make more of a picture, this is the normal key exchange process that's done between two VPNs when establishing an IPsec VPN. And importantly, you can see that if I have an QRNG source or strong random source, I can share it in advance with the two VPNs. So it's a pre-shared post-quantum key, and mix that in and result in an AES 256 key that is considered quantum secure. And importantly, NSA has come out and said, this is such a great idea. We're going to specifically create an annex that describes how to securely and robustly share these keys, because the whole point of you can steal it along the way, then you can compromise it. So NSA has gone so far as to actually give explicit implementation guidance on how to do this the right way so you don't undermine all of your good work. And this isn't some, again, esoteric concept. If you use Palo Alto, Cisco, Fortinet, Juniper, or Red Hat, and others for your IPsec VPNs, they already provide support for this standard. You're just not using it. So why not use it? It takes just minutes. And in fact, we're really proud to say that we've partnered up with Palo Alto Networks and created a PPK generator that can be plugged right into your PAN-OS, whether it's a physical or a virtual firewall. And starting with last year's release with 11.1 of PAN-OS, you can now direct import from Entropy using our PPK generator. We've timed it from the time I said, man, I'd like to do that, to the time I've upgraded my firewalls, 5 to 6 minutes. So if you can move your IPsec VPNs to a post-quantum certified status in 5 to 6 minutes, what are you waiting for? You could probably do it before the end of this webinar. And so there's a QR code if you're interested in signing up and getting access to that for a free trial. I'm happy to share it and get people excited about the migration to post-quantum security. The same solution will work with those other vendors, as I mentioned. So another use case, it's got a little bit more broader appeal, especially if you're working in virtualized environments, is directly injecting quantum entropy into the base operating system, whether it's desktop, server, or especially virtualized environments. And the net result is by replacing the entropy device that the OS is pulling entropy from with a kernel device powered by strong random. Now everything above the level of the operating system automatically starts with that quantum or strong entropy. And as a result, I don't have to change versions of anything. I don't have to upgrade to new algorithms. I don't have to recode anything. As long as they're using system random has now gone from PVC to stainless steel. And I have to give a tip of the cap to Red Hat. Their engineers are the ones who've kind of really laid the groundwork for this pattern, especially in virtualized environments, whereby injecting the random into the base OS, all the hosted OSs, regardless of what they are, inherit that strong entropy. And we think this is just a fantastic pattern where just by dropping a device driver onto a target device or server or operating system, boom, instant, seamless, transparent upgrade to strong entropy, and therefore the strong cryptography, letting each algorithm, whether classic or quantum, operate at its full strength. We think that that is a very powerful and a very easy deployment use case because it's just a small OS patch. Now, importantly, everybody uses clouds. Everybody uses public SaaS. And importantly, all the major SaaS and cloud providers have a concept, and they have different names because everybody's got to be slightly different, whether they call it a custom managed encryption key or CMEK or a BYOK, bring your own key. They all have a mechanism where you can define and use your own cryptographic keys. That is fantastic. And importantly, starting almost 2 years ago, as an example, Amazon S3 says whether you like it or not, every blob you put in S3 is encrypted. So nothing is ever stored in plain text. But the question becomes, which cryptographic key is used? If you don't specify one, Amazon gladly generates one for you. But they give you the mechanism where you can generate your own. And so therefore, why not take complete control? Why not know? And again, I'm sure Amazon's using absolutely fantastic entropy. I have no reason to believe that they're not. But you can use your own entropy. You can have complete control over the strength of that key. And as a result, it introduces this concept we think is super important, which is entropy sovereignty. If you think about data sovereignty, where you want to control where your data sits, who has access to it, where it's produced, where it's consumed. And the same thing is with your source code, right? We've seen supply chain attacks on source code. Well, what about a supply chain attack on entropy? What if the entropy source you're using, especially if it's third party as part of a public cloud or public SaaS, is compromised? Well, then so is all of your data and so are all of your systems. And so we really believe that from an IT perspective going forward, we're going to start to see the same rules that apply to data sovereignty and source code supply chain security to entropy security. And so therefore, this becomes a mechanism, and it's scriptable. I think it took our team 5 to 10 minutes to write the script so that instead of using the default Amazon key, we could pull it from an entropy source like our service and plug it right into the public cloud. And again, when it's an as a service model, that makes this integration very straightforward, very easy to implement, very easy to maintain. Who doesn't love easy? And this importantly gives the IT, the CISO, and the CIO 100% control of their own cryptographic keys, which means they've got control, they've got authority, they've got responsibility. couldn't ask for more than that. And again, you name it, they support it. So this isn't a one-off or an exotic. This is a utility waiting to be leveraged. All you got to do is put in the hustle to get it done. I alluded to this earlier, but we're starting to see a lot of implementations. They're still mostly at the proof of concept, though. We're starting to see some scale and some commercial offerings using quantum key distribution, where I use a fiber optic infrastructure to entangle photons at a distance, and the net result is that entanglement generates noise, aka entropy, aka randomness, that can then be used as cryptographic keys. And the power of this is that quantum entanglement is intrinsically safe. It cannot be compromised, because if you compromise it, you break it, and the net result is the evil attacker can never access that channel. And we think that is really exciting. Because it's early days, it's still somewhat expensive, relatively speaking, to digital mechanisms, because we're still, the technology is still being developed. But like all technologies we've seen, it'll follow that nice curve of, as it scales, costs will drive down, and this will become very practical in the next 5 to 10 years as yet another way to do it. And the great news is there is a standard interface for this called EC-14, and a number of VPNs from Cisco, Fortinet, and others already support that interface. So that if you want to leverage or test with quantum key distribution, you can today by marrying that quantum key distribution infrastructure with your existing VPN vendor. And so it's more of a, slotting together the two components rather than some custom build or some novel solution that becomes brittle and hard to maintain. And it's standards based. And just like whenever there's a physical implementation, there's always a digital. And so we're starting to see a number of solutions around digital quantum key distribution, where instead of using quantum physics for the distribution, I use strong symmetric, whether it's classic like AES-256 or a quantum algorithm like Entropy's Keep or others. The idea being use strong digital encryption to move those keys and synchronize them across nodes. Again, the same kind of tiered architecture. You have physical generation, you have quantum secure, some synchronized distribution, and you then have that EC-14 standardized interface, so you can interchangeably. And we really see digital quantum key distribution being the last mile, because putting a fiber optic connection into my iPhone is not going to happen anytime soon, but being able to use through the core networks, photonic QKD, and then use digital QKD to the desktop or the last mile over the air, that gives us a lot of flexibility to really cover and go wall to wall with quantum key distribution. That also then leads to other use cases where, again, on-prem and cloud, where I can now synchronize encryption keys between my on-prem devices like a Luna HSM from Thales to the key management solution of my public cloud, say Azure Vault or one of my SaaS providers. And because it's all digital, I can now have that on-prem hardware synchronization with that off-prem software key manager. And we've talked to several banks that have teams of people whose whole job it is to do this key synchronization. And do you want humans doing key synchronization? Is that a good use of your IT and security talent versus allowing for these quantum secure mechanisms that are standards based and already available to be plugged in, solve that problem, automate it while securing it and taking human error and human labor out of the loop? What a fantastic solution. And again, vendors like Thales already support the interface. The cloud vendors already support the interface. All that's left to do is assemble the parts. And one more example where maybe the software at scale may make a difference there. In this case, with symmetric encryption, there's this idea of an initialization vector, or IV, that's used to help preserve the use of a cryptographic key longer, whole story in cryptography. If we want to go down that, we'll have another webinar on preserving your cryptographic keys. But just take my word for it, this is a standard mechanism. But you need a lot of it if you want to do packet level IV, which is the strongest, where for every packet I send, I change the vector. And for example, with 5G networks, you would need about 32 megabits per device in order to secure the packets associated with 1 gigabit data streaming. And then from the base station to the core, you need about 32 gigabits per second. No hardware device. If we're spending $6,000 to $10,000 per gigabit, that would be a lot of money per base station. So that's where a pseudo quantum random number generator at high volume would kick in and give me that entropy expansion, give me the ability to solve this. So again, hardware solutions, software solutions, there's always a way to find the right result that will give you robust security over and above what you have available today. So I will wrap this all up, and then we're going to go to questions next by saying this is a rising tide, and we are asking for folks that are excited and interested in helping to advance the standards, helping to advance the science, helping to advance the adoption, to join what is currently called the Quantum Entropy Alliance. It's a consortium of a number of vendors across the hardware and software landscape that are coming together to advance the whole space. And so, of course, like any community, the more the merrier. So it's an open call for anyone who'd like to join. So please, if you've attended this today and you want to learn more and you want to participate and help broaden the acceptance and the use of Entropy to make sure we all have robust security, let me know. And so with that, I want to thank everyone who attended today. Here's my contact information. If you'd like to email me, you can of course check out Entropy. And if you scan that code, we're more than happy to let you get free access to Entropy as a service, so you can kind of kick the tires, see what it's all about, and learn more about it and see how it can fit into your business and IT and security environment. So again, thank you very much for your time and attention today.
Thank you, Michael. That session was really informative. Now it's time for the Q&A session. So please send in your questions to the panel and we'll answer your question as per the time that we have available. So starting with the first question that we have, a 0.5 entropy rate appears to be good today, but will I need an even higher entropy rate in the future as the attacks get stronger?
That's a great question. There's always a theoretical limit of a entropy rate of 1.0, where every bit is truly random. But as hopefully came across in the talk, we don't live in a perfect universe. We just approach it as close as we can get through different techniques, hardware and software. So, I think it'll probably evolve. And yes, you might need higher levels, a higher entropy rate over time, just because there's literally billions of dollars being invested in machine learning and AI. So the weapon side or the attacker side is going to continue to get more cheaper resource. And so, what that timeline looks like, I don't know, but I would say get to the floor now. If you're not at 0.85 across your various sources, level up to that, because that will buy you the time, and then you can, of course, continue the upgrade cycle as again, it's always with cybersecurity, cat and mouse. As the cat gets stronger, the mice finds new tricks, and so we'll see it evolve. But I would say, just gut check yourself and say, are you already in a good posture? Because if you're not, get that done first before worrying about getting even further strength to your entropy rates.
Great. So moving on to the next question. In the context of rising cryptographic threats, how does entropy rate impact the longevity and security resilience of cryptographic algorithms, particularly in environments with limited resources or constrained devices?
Well, and I think I tried to almost to be a broken record on the point that without a good entropy source, doesn't matter how awesome your algorithms are. And so it really is something where it wasn't a topic before because the weapons didn't exist, or the ability to just read the internet, right? Read 250 million websites, in a trivial manner and analyze their certificates for strength and run math on them to see if you could break them. That would have cost, who knows how much money. Now it's like pennies. And so, it's one of those things where you have to think about it. And resource constraint, I think was in that question, is a very serious consideration because, devices, especially consumer devices, outnumber IT devices and managed devices, probably 10 to 1, 20 to 1. Who knows how many, again, do your network scan at your house and just see how many dozens of devices pop up as connected to your Wi-Fi. And so it all comes down to, but each one of them are to some degree, hardware-wise, at least frozen in time. You're not going to go get a screwdriver out and open up an Alexa in order to insert a random number generator. So that's why we really think that from a brownfield, protecting the legacy install, software approaches are a necessary tool in the toolbox. Because we've even seen historically things like, distributed denial of service attacks from baby monitors, right? Because they had such lousy protections, they could be harnessed for bad purposes. And so there's just quite a bit of frailty out there. So the software gives a great option, but when you can get it and you can get to a hardware source and it makes sense for your product or service, heck yeah, you should do it.
Okay, great. So the last question that we will be taking up today is, considering the complexities of implementing QRNG, what are the potential security implications of integrating QRNG hardware at scale within a cryptographic infrastructure, particularly for enterprise level applications?
Well, the challenge with anything to do with security is it's like the old first do no harm. And so adding new, maybe seemingly exotic elements to your infrastructure, to your enterprise architecture, is automatically met with some nervousness, because the risk is that that the cure is worse than the disease, that you're going to introduce a new vulnerability through complexity or through a bad implementation. But I guess I would suggest, and I hope I gave plenty of examples, and seeing the number of vendors that have emerged in the space with a lot of different form factors, I hope there's comfort for folks in the fact that there is a mature industry. There are standards-based approaches, which I said about 82 times in the talk, but hopefully that came across, that this isn't something you're doing as a science project or you're out by yourself, right? ETSI 14, RFC 8784, a lot of internet engineers have spent a lot of years thinking about this, paving that groundwork. So we think, therefore, it is very achievable. And again, falling back on standards, on the NIST standards and others, again, gives you those checks and balances to make sure that the choices you're making are intelligent and that you are on a robust pathway to get to where you want to go, which is stronger cryptographic security without introducing new IT risk. And I think that the great news is if you asked me this question 5 years ago, I'd be like, well, you're pretty bleeding edge. Well, we're not bleeding, now it's leading. And especially when it comes to advanced security and with the rigorous advance of AI-based attacks, you want to be a leader in these kind of upgrades. You don't want to be a laggard, because ask the people who lost $30 million in Bitcoin because they didn't upgrade. Whoops, that's the laggard position.
Okay, great. So these were all the questions that we had for today. I just want to thank Michael for his thought-provoking insights. And if there's anything that you want to learn more, we do have some attachments from Entropy that are attached over here. So you can get started with quantum entropy. And if you have any questions, feel free to reach out to Michael or the Entropy team. And thank you everyone for joining in. We've got one more session for today, so stay tuned. Thank you, Michael.
Thank you very much. Thanks for having me. Thanks everybody for joining.